Okay, up to this point, all we were talking about was the source, which would be a battery or the current source, and a resistance. Everything we had so far was very simple. So, except for the source, either battery or the uh, current source, the only thing else we have so far was the resistance. And as I said, we showed them in form of the resistance was we have it, for example, like a lamp, like the electrical oven, like the electrical heater. Usually, you have the elements in resistance that get the energy from the sources and convert it to the mostly heat or sometimes light. Uh, as I said, like a lamp or like the electrical oven. So you provide them the energy, and they only consume the energy uh, and change it to another form of energy. So um, what we had here, so here, for example, it was the source that we have, and then we have, for example, a resistance. So this was the resistance what we had. As I said, the resistance only use energy. There are two other elements that we are going to talk about. It first, I will talk about the one is going to be the capacitor that we will talk about it, something like that, and we show it like that. And then we are going to talk about another element that is going to be the inductor, which later on I'm going to talk about that. And we see how these two new elements behave in the circuit. So this one, yeah, this one, uh, this is the sign for the capacitor, and this one is the sign for, let me choose another color, inductor. I will talk about this one later, but today I'm going to talk about this one in detail. Remember, just before I started, so we have the sources that provide the energy. It's going to be battery, or it's going to be the current sources, or whatever source we have. It provide the sources. Then we have the resistor here. Then we have these, the resistor here that only use the energy. The only thing the resistor do is just resistance only use the energy. They are not doing anything else. So you give them energy, they convert it to something else. These two new elements, the capacitor and inductor, they're not providing energy, they're not using the energy. They just temporarily store the energy. That's all they do. They store the energy and then they release it. The same here. It stores the energy and then it releases it. The difference, you may say that, okay, what's the difference between the capacitor and the battery or the inductor and battery? The difference is that the battery can store lots of energy and then release it. The capacitor can, or the inductor, in the other words, they can store the energy very fast and they can release it very fast, but they cannot store or store the energy as much as the battery. So in the battery, you can store lots of energy, but you can release it over time. Capacitor and inductor is like that. They can store the energy instantly. They can release the energy instantly. So they can't store as much as energy that you store in the battery, but they can be store or release energy very fast. So it's like they behave like a battery that can be charged or discharged very quickly. They behave like that. So they are not a battery, but they behave like a battery that can be charged or discharged very quickly, instantly, but they cannot hold lots of energy. That's the main difference that they have. So again, if I want to say the battery provide the energy, the resistance use the energy, The capacitor and inductor just store the energy momentarily, temporarily, and then release it based on the condition of the system. So later on, when we are analyzing the system and we want to calculate how much the power is consumed or how much power is provided, remember that these two, they are not using the energy, they are not providing the energy. They just store, release, that's all they do. So let's first look at the capacitor, and then again later we go and look at the inductor. So when we look at the capacitor, basically what we were dealing with is the two layer of let me say put here for example have two layer of for example some kind of material, and then we have which is going to be separated by some kind of insulator. So for example so you have two plates of material that are conductor, and then you have this material inside between them. There's going to be somehow I would say insulator, so it doesn't let anything pass through. So you have two plates, and then you have the insulation between them that doesn't let anything pass through that from that plate to other plate. And then you connect these two plates to I would say for example the battery or the sources. Now by the time that you have the current goes toward that, so you, for example, you connect it to the battery, and then let me go ahead and connect it to the battery. So assume I have the battery sitting here. Go there. Oops. Then I have a key. And it goes there. It goes here. It goes there. So as long as the key is open, nothing happens. But as soon as I go ahead and close the key, so go ahead and I close the key, then there's going to be a current in that circuit. So when we have the current start to move from this positive one and goes all the way. So we have the current goes from here to here. What's happening here is that we have the positive current comes and start to build up on this plate. So as soon as the positive current start to build up on this plate, they are gonna push away the positive charges from that plate away. So the positive current start to build up here. Because we have the positive here, you know that if you have the positive sign is going to push away the positive, the negative is going to push away the negative. So we like the magnet, if you have, for example, the magnet, the same side of the magnet is going to push away, for example, the same sign. The opposite sign is going to, in the magnet, the opposite sign is going to attract each other. What we have the same sign is going to push away each other. So if I have the positive charges build up here, these positive charges start to push away the positive charges from the other side, and it causes to have the other side become only the negative charges remain. So the positive charge start to leave that other plate, and only the negative charge So by the time these I keep adding the positive charge, I'm gonna get push the positive charge from the other side. Again, I keep adding the positive charge, I keep pushing the positive charge away, and I have the current. But until I get to the point that I push all the positive charge away from the opposite plate. When I get to that point, that all the positive charge moved away, then at that point, the current becomes zero because there's no more charge is going to go through. All the charge go. So it's going to be like that. As I open it, as I close the key, the charge is going to start to build up here. And these charges start to push the current, the positive charges here to move. So at the beginning, I'm going to see the current goes through my circuit. But as the time goes on and I'm going to build up all the positive charges here and all the negative charges here, there's no more positive charges left on the other plate to push away. At that point, the current becomes zero. And eventually, it doesn't let anything goes through. So this this capacitor, at the very start that I close the key, doesn't do anything, let all the current pass through, and eventually start to behave as an isolator, and then eventually it cut the current. There's no current go through any further. When we get to that point that it doesn't let the current move any further, it's when we have our capacitor fully charged. At that point, although it doesn't let the current goes through, but because one side of that is positive and the other side is negative, it's going to be fully charged. So now, in any case, if I remove in this case, if I remove the battery and connect them, so assume I go ahead and open the key. So I go ahead and open the key. It's already charged. And then I connect these two ends together. Then it's gonna give me a current in this loop. And how it's gonna give me the current? It's gonna start by pushing this positive sign. It goes, you're gonna have the current goes all the way through here, here, and here, and goes back. So all the positive start to move here to that other end of that until all the positive charges goes that negative charges, and then it becomes neutral. So momentarily, that will happen in flash of seconds. So it happened very fast, but momentarily, it's going to release whatever energy it stores back to the circuit. So that's how we use it. Either we use it to store the energy or we use it to release the energy it already stored in the circuit. If you want to consider it as a, I want to give you a simple example. That's how it actually, for example, work. I can give, for example, to assume that have a pump, so the water pump, and the water and this pump is gonna push the water to the tank, and there's a valve in here. So it's not exactly the same idea, but it's very similar, so you can figure out what is happening here. So if I open the valve and assume, for example, my the income of the water is going to be larger than the water is leaving. So if I open the valve and let the pump work. So if I, for example, I open the valve, let the pump work, it's gonna push the water into that tank, and then a little bit water leaves that. Over the time, because I'm gonna just add the water to that, it's gonna keep adding and adding and adding the water in the tank. So you're gonna have some water stored in the tank. Now, if I go ahead and close the valve, then the moving the there's not going to be any current getting into the tank, but still, because you have some water stored in the tank, those water that is stored in the tank is going to still provide the energy to the output of that tank. And then if I go back again and open the valve again, so basically so it's gonna I'm gonna just, the water is still going out and going out and going out, and we're gonna have the water still, the surface of the water is going to drop and drop and drop, but we are still have the outflow. And then if I open the valve again, if I open the valve again, I'm going to have the water goes back in, and then again the surface starts to move up. So although I keep closing and opening the valve, but the output the output of the water is not going to be disturbed here. Although there is some disturbance in the input, there's no disturbance at the output here, because I have some water stored in the tank. And whenever the valve is open, so the water comes to the tank and leaves. Whenever the valve is closed, the water still leaves the tank from the water stored in the tank. Unless I keep the valve closed for a long time, so all the water in the tanks is gonna eventually leave the tank, and then it becomes dry. This is how it works in here. So when I have the battery, it's going to, I store some charges here over the time. And if I disconnect it, or I connect the other two end of these to other sources, is going to release the energy it stores to other elements of the system. So that's how this capacitor works. So it's going to be store the energy very quickly, and it's going to release the energy as well very quickly, and then we use it for any purpose that we need in this system. So if we want to look at how much energy or how much charges we are going to store in the capacitor, I would say that some of the relation for the capacitor. So look at the stored charges in the capacitor, and then the voltage or current in the capacitor. The stored charges in the capacitor come from the Q is equal to C, and then the voltage across the capacitor. So the Q is the amount of charges that the capacitor hold, and C here is called the capacitance. And they're showing it, the unit of that is farads, and usually they show it with the F. So it's the unit of that, and that's the voltage. So that's the charge. So that's the charge, and that's the voltage across the capacitor. So that's how it works. This is one equation that we will use in the capacitor. And another equation that we use is the current through the capacitor. As I said, the current in the capacitor is going to be, again, the capacitance, the same as here, and it's going to be dV divided by dt, the change in the voltage over the time. So look at this equation. If V is constant, If V is constant, it means that dV over dt is 0. It means that the I is 0. So if we, that's what I discussed before. If we connect the capacitor to the constant voltage, it does not let any current goes through. It takes a very quick seconds. It's very, probably not seconds, very fraction of seconds to be fully charged. And after it's charged, it doesn't let any current goes through any further. So if we want to have the current goes through capacitor, the voltage should change versus time. If the voltage does not change versus time, then the current does not go through. And it's basically behave like an open circuit. So you can assume that's not there because it doesn't let any current go through that to that wire that hold the capacitor. So these are the two equations that we'll have here, and then just by rearrange these two equations, we are going to get that, can say the Q respect to the time is going to be the integration of the I it dt and plus the Q at the time 0. This is another equation we can get from the combination of what we already know. And then the voltage also is gonna becomes 1 over C, again, integration of IT dt, again from the T0 to T1, and plus the voltage at time 0. So these are the, I would say the color equation that we have here. So it's the one of them here, another one here, then we have this one here, and then we have this one here. And as you can see from these equations, we're slowly needs to move to the parameter that's going to be time dependent. Up to this point, most of the things, almost all the things we have was independent of the time. They were constant through the time. But from this point on, we are slowly start to consider the conditions that they're going to be time dependent. Because, for example, here, let's say if it's not time dependent, then nothing is going to happen there, except for very start that we open or close the key. That's we actually have some change in the voltage. After that, when the voltage becomes constant, then there's nothing going to happen in our system. So that's one shift we are going to do from this point on. Slowly look at the how the time-dependent currents behave in our circuit. Okay, let's look at an example and see how these things works. So the very first example I'm gonna look at it. It's gonna be a simple. Assume we have a simple circuit here, and then we have these. And then we have, so we have a battery connected to the capacitor, And this time we assume the battery is going to be time dependent, so it's a function of time. The voltage is going to give us function of time, and let's see how it behaves. So here we have this, the capacitance is going to be 1 microfarads. And remember, the farads is a very large number, so usually we get the number in case of the microfarad, and the micro is 10 to the power of -6 when we discussed it previously. So whenever usually we see the microfarad, and whenever you have the micro is 1 times 10 to the -6. And then we have the I goes through that circuit, and then the I is going to be also the function of time in that circuit. And if at this point we are going to have the, so if I go ahead and assume I have the voltage, yes, so the voltage is going to be time dependent. So assume I have the voltage, and it's going to be the voltage as a volt, and then I have time as a microsecond, and then let's see if the current, the voltage change as, let's see, 1, 2, 3, 4, 5. So if the current goes here from 0 to 10, so if the voltage goes from 0 to 10, it stays constant here and goes back to 0. So it's going to be 10. That's going to be 1, 2, 3, 4, and 5. So assume our voltage change like that. So it's going up, stays constant, goes down. If we have something like that, we want to see how these current and voltage of these, basically the current and charge in this is going to be changed. So the voltage is time dependent. It increase, stay constant, and decrease. And then we want to go here and look at the effect of that on this circuit. So we know that the Q, okay, we know that the Q is the C times V. So if we have the V value, we just can go ahead and times it by C to get the Q value. Before I say how we are going to do that, I'm going to just show you, and we are going to use it a lot. So you probably know this from the geometry, but I'm going to say that again. If I have 2 points on the line, so if I have an XY axis, X, Y axis, and I have 2 points on that, it's going to be x1 and y1 with the coordinate of x1 and y1. And the second one is going to be x2 and y2. It's going to be x2 and y2. Then if I want to find the equation of the line that passed through these 2 points, the equation of the line that goes through these 2 points is going to be y minus y1 is equal to y2 minus y1 divided by x2 minus x1 times x minus x1. So this is the equation of the line that goes through these 2. It doesn't matter it's going up or it's going down, it's going constant, it's all like that. The y minus y1, and then this is the slope of the line we have, y2 minus y1 divided by x2 minus x1. So this is the slope, and then it's going to x minus x1. So that's how we write the equation of the line for that. So here we need to write the equation of the line for this voltage one. So we want to see what's the voltage changing here. So for the voltage at the here at the beginning, it goes from start from this point, which is going to be 0, 0, and then it goes to 2 times 10 to the negative 6 and 10. That 10 to the negative 6 comes from the microsecond because it's a microsecond here. Everything is in microsecond. And then the y value. So for the first one, so I'm going to write it here. So the voltage here, again, y2 minus y1, so it's going to be y minus 0, because y1 is 0, is equal to y2 minus y1, so y2 is 10 minus 0. And then x2 minus x1, so it's going to be 2 minus 0 times to the negative, so 2 times 10 to the negative 6 minus 0. And then you have x minus x1, which is going to be 0. So this is for the t between 0 and 2 microseconds. And then we have v is the constant value of the 10 here. For t is going to be between 2 to 4 microseconds. And then we have here again, we have here, the coordinate here is 4. It's 4 times 10 to the negative 6. So x is 4, and it's going to be 10. And then coordinate here is going to be 5 times 10 to the negative 6 and 0. So again, y2 minus y minus y1. Y1 is y1 is 10. So y1 is 10. y2 minus y1, so y2 is 0, y1 is 10, so it's going to be 0 minus 10. x2, which is going to be 5, minus x1, which is going to be 4, so it's going to be 5 minus 4 times to the 10 to the negative 6. So 5 minus 4. And then you have the x minus x1. So, and you have the x, and the x1 is 4 times 10 to the negative 6, and it is for the t between 4 and 5 microsecond. So now we have the equation of the v, so we know the v, this is the v's. And then by knowing these are the v's, so we can go ahead and look at this equation. So q is the cv, so basically q is c is it 1 microfarad, which is 1 times 10 to the negative 6 times v. So this is how the q is that. So if I go ahead and times each of these equations by 10 to the, it's negative 6. So if times each of these by 10 to the negative 6, I'm going to get the value of the q. So basically the q is here. So this one is going to be y is equal, so it's a 10 divided by 2 times 10 to the negative 6, and it's the x, and then times 10 to the negative 6. So it's going to be the q. And so here probably it's better that instead of using y and x, I'm going to use the v and t. So it's probably better to use it that way. So I'm going to replace all the Y with the V. So it's going to be V, it's going to be V, it's going to be V, and all the X value with the T. Just replace the X value with the T. So let's replace it with the T. And the same here, I'm going to replace the X value with the T. So everything is now is gonna between the V and T. The same here, I'm also gonna replace the Y with the Q and the X with the T. So again here, just for it's gonna be T between 0 and 2 microsecond. And then here again, I have the Q is going to be 10 times 10 to the negative 6. Again, between 2 and 4. And then I'm going to have the cube for the last. So this one. So I have to rearrange it before I actually times it by 10. So it's going to be 10 and divided the 5 minus 4 is going to be 1. So it's going to 1 times 10 to the negative 6. And it's going to be t minus 4 times the 10 to the negative 6. And I bring the negative 10 to the other side, negative, so plus 10. And then I times the entire one by 10 to the negative 6, 10 to the negative 6 to calculate the cube. So it's going to be between 4 and 5 microsecond. So this one, I rearrange this one to first to find the V and then times it by 10 to the negative 6. So this is the Q that I have. And then if I want to find the I, you remember that, again, I'm going to write the rest here. The I is going to be C dV over dt. So if I go ahead and calculate this, just C and dV over dt, so it's going to gives me the I here. So if I write the I here, I'm going to write it here. So this is the V. So it's going to be 10 divided by 2 times the negative 6 t. So if I calculated dV over dt, the I here is going to becomes, and you can do that. So it's only this constant here because this t is going to go away. So it's going to be 10 divided by 2 times to 10 to the negative 6. For the second one, if dV over dt is going to just come 0 because it's constant. And for the third one, so if I rearrange it, which is going to become this one, and do the integration, the only thing is going to comes out is going to be 10 to 1 times 10 to the negative, if I'm right. So only these constants stay here. So only the, yeah, so that part is going to go away, that plus 10 is going to go away. So the only thing is going to left is this coefficient here. So it's going to be negative 10. So I missed the negative sign here. So it's going to also be negative here. So there's a negative sign here, I forget. So it's going to be negative 10 divided by, it's going to be negative 10 divided by. So this is going to be, if I calculate it right, so these are going to be the I value that I have. Now try to, so this is the V I have. I try to draw them as well. So I try to draw the T and this Q. If I consider as a microfarad, so the micro C. And then if I draw the I beneath that, it's going to be T, it's going to be I as an amp. See what we are going to get. So again, if I consider the 1, 2, 3, 4, and 5, it's going to be 1, 2, 3, 4, and 5, and these are going to be all microsecond. It's going to be microsecond as well. So if I go ahead and try to draw, if you go ahead and draw these three equations, this is what we are going to get. It's going to be similar, like so it's going up, and then it's going to become 10, and then it's going down to 0, and it's going to be at this point it's going to be 10. So it's going to be 10, and because I put the micro here in the units, so that 10 to the negative 6 goes away. And then if I draw the current here, what I'm going to have, so it's going to have becomes, let me see, so for the current, oh sorry, for the current I forget the C, so it's the C times dV over dt, so I have to times all of them by C, so it's going to be all of them times by 10 to the negative C, because this is a C, and it's going to be 0 regardless of that, and it's going to be times to the 10 to the negative 6. So this value here, I write it other, so this value is C, this value is dV over dt. The same here, this value is here is C, this value here is dV over dt. So if I times it by 10 to the negative 6, so it's going to, these two goes there, so it's going to be 5 here. So have it as a 5, and then it becomes 0. Try to make it so it becomes 0, and then here this by this cancel each other, is going to be negative 10. So it's going to look like something like this, and then go back there. So it's going to be comes at the 5, and then it's going to comes at the negative 10 here if I want to have them. So if you look at that, so these are just the simple maths. You can go and do that, and these are again just I'll draw this equation, nothing special. You can draw them very easily. But you see that here when we have the voltage changing and increasing, we see that the charge is built up on the capacitor. So the voltage increasing, the charge is going to build up the charges, and as throughout the time that we have charges is built up, so we'll see that the current is going to pass through that capacitor. And then as soon as the voltage become constant, then the charges become constant, and they said doesn't let any current goes through. So as soon as the voltage become constant, is like becomes the open circuit. It doesn't let anything go through any further. And then as soon as the voltage starts to drop, you will see that it's gonna start to release its charges. Basically, in this part that the voltage increases, it's charged, it stores the energy. Then when the voltage is constant, it doesn't do anything. When the voltage is going to drop, it's going to release back the charges it already stored, release them back to the circuit, and then you will see the current is going to become negative 10. And the reason is that because the voltage is dropping, this starts to release its energy, and the energy is going to be released is going to be the opposite of how it's gained it. So it's going to release it backward to the system, because the positive is going to be all, for example, here, when it's charging, this end is going to become positive. And when it's starts to discharge, this positive is going backward. So the current starts to go backward and everything becomes, so it's going to be negative. So here is charging, here doesn't nothing happen, and here is discharge and release the charges back to the circuit. Let's look at another example. This is going to be how similar to how these things work. Assume that we have the just assume we have a capacitor. That there's a current going through that capacitor, and that capacitor has the C is 0.1 microfarads. So, and then the I is going through that, and it's going to be function of time. And in that case, if I know the I, the I is equal to 0.5 sine 10 to the 4 t. So assume that I have a capacitor, I go through that, and then the I is the function of time. And then we want to see how much is going to be the charge and the volt in this capacitor. So we know that the charges, we have the equation. So the charges was, the equation we have was T0, T1, the integration of the I, T, dt, plus Q at the time of 0. So T0. So this is the equation we have. If we assume that there is no current at the start, so assume that at the t is 0, so there's no current. You can see that if I put the t0, this one becomes 0, so the everything becomes 0. So the I t is 0 is 0. So if I started from the t0 and go to, I'm going to do it parametric. So if I start from the t0, the IT is going to become 0. So there's no current at the beginning of that. And because there is no current at the beginning of that, there's nothing there. Also, we assume the Q is 0. So at the T0, assume current is 0 and Q is 0. It's completely discharged. Nothing is there. And then we'll see what happens. So the Q is going to become from 0 to T, and the IT is 0.5 sine 10 to the power of 4 T, and plus the that Q0, which we assume is going to be 0. So here, let me put it here. So we assume the Q at T0 is also 0. So this is the Q. That will the simple integration. So you can, and if you solve that equation, so you're going to get negative 5 cosine 10 to the 4 t, and then you have to use it between 0 and t. Sorry. So also this one goes, so it's negative 5 times 10 to the 4 cosine 10 to the 4 t, and it's between t is 0 to t is equal to t. And um, let me make sure that I have everything right. Oh, yeah. So it's going to be this one. Yeah. So if you replace everything into that, so you will eventually get the Q. It's going to be 0.5 times 10 to the negative 4. It's going to 1 negative cosine 10 to the 4 t coulomb. So it's going to be the Q. And then if you want to calculate the voltage, we know that the Q is C times V. So the voltage becomes Q divided by C, and the C is that. So the voltage is going to be, so this is a Q, this value here. So I have 0.5 times 10 to the negative 4, 1 minus cosine 10 to the 4 times t, and then divided by c's, which is going to be 0.1 times 10 to the negative 6. So it's going to be the value of the voltage in this capacitor. So it's how the charge is going to be in there, and how the voltage is going to be there. And let me see if I can show you the graph of that. So for the equation that we have is how the going to be. So the current is going to be the sine. So it's a sine equation. So you see it's going to go up and then goes down. And then the charges is going to behave like that. So again, it just have the it was a cosine function. So that cosine function is going to look like this. So it's a start from 0 when the current is 0, and it's going to reach to its maximum when actually that current becomes 0. And then when the current changes its direction, so you see here the current is positive, positive, positive until it becomes 0, and then it becomes negative. As soon as the current changes its signs, the charge starts to drop, and the same as the voltage. As soon as that we have the current is the positive, the voltage increases. Or when the current reach to 0, when the current becomes 0, so these two reaches to their maximum, and then when the current reverse, then they both the charges and the voltage starts to drop. Okay, now I'm gonna start talking about the power and energy that's gonna be stored in a capacitor. As I said before, the capacitor and the same as the inductor, they are the elements that they are not using the energy, and they are not producing, they're not providing the energy. They just store the energy and release the energy. So in case that we want to know how much energy, if we have the capacitor in circuit, how much energy is going to be stored into that, or how much power is going to be stored, that has a equation that for the power, remember, as we had also for the resistance, power is always like that. So power is always the voltage times the current. So it's going to be V times I. Power is always like that. Now if the V or I are constant, so this is going to be constant, or if they are time dependent, which in most cases for the capacitor and later on for the inductor, we see are the time dependent. So they're just going to be Vt. So each of them is going to be just time dependent of that. So the Vt times I T. That's the equation for power. Regardless, we have the resistant or capacitor or later on inductor. This is the power. So always the power equation is this, and so it's the power that we have. For the energy, which the book shows with the W, I'm going to just show the W as well. So the energy in the capacitor, again, assume is the time dependent, is going to be half of the capacitance and times the voltage square, and assume the voltage is function of time. And if we have the equation we use the equation before for the between V and C and the Q, the charges, that we can rewrite this equation as again half of the voltage times the charges in the capacitance, or we can write it as again half of charges squared divided by C. So you can write the energy or obtain the energy with any of these three formula, either one. So if you have the C and V, we use the first one. You have the V and Q, we use the second one. If we have a Q and C, we use the third one. But for the power, that's it. It's always V times I, and that is what we use for calculating the power. Now let's look at an example to see how we can actually calculate the power and the energy for the capacitor. So assume that we have a capacitor that the voltage along that, so assume I have a capacitor, something similar like that. Whatever, so it's going to be connected to whatever, so we don't know the rest, but assume we have a capacitor like that, and we know the voltage in that capacitor is going to be Vt, and and the capacitor itself is 10 microfarad. So this is what we have, and then we want to see what's happening in that capacitor. Assume that we know the voltage, the Vt, for the first 5 seconds of that, for first 5 seconds is going to be, assume it starts from the 0, so the Vt assume is going to be 1000 T. For the if a T is between 0 and 1, and then it's going to be again 1000, so it's going to be constant volt for if it's going to be between 1 second and 3 seconds, and then it's going to be 500 times 5 minus T volt for the T is going to be between 3 seconds and 5 seconds. So we know the voltage across this capacitor is going to be changed as this. Now I want to calculate the power and the energy into that. So remember that the power is the V times I. So it is the voltage times current. So if we want to calculate the power, the very first thing we need to calculate is the I. So we can use that. So if this is the V, then we are going to say that the I, we need to calculate the the I, and remember the I. So let me write it a little bit up there. So the I in the capacitor is C and dV over dt. That's the I. So if we want to calculate the I, we can use this equation to find the I. So if I use that equation, so the I in T is going to be again. So for the top one, so if the C is 10 times 10 microfarad, so it's going to be 10 times 10 to the negative 6. So this is a C. And then dV over dt here is going to be 1000 times 1000. So it's going to be, for T is going to be between 0 and 1. And then here again, for the second one, then the C is 10 to the 10 to the negative 6 times dV over dt. Here V is constant, so dV over dt is going to be 0. And we had it before. If we had the constant voltage in the circuit, there's not going to be any current in that circuit. So between 1 and 3, let's not look like D. So between 1 and D, so it's going to be 0. And then for here, again, C, the magnitude of C is 10 times 10 to the negative 6. And then this one, if you get the dV over dt, so the first term is going to be 0 and the second term is going to be negative 500. So you're going to times negative 500 for t between 3 and 5 seconds. And that we have. And then we can even simplify that further. And so this is the I. Now that we have the I, we can go ahead and calculate the P. So we know that the P value, as I said, P, the power is always the power is always voltage times current. Oh, sorry, it's T, the voltage times current. So here I just need to multiply these two together to get the P value. So the P times T is gonna be, again, so between 0 and 2, so I have 1000 T here and this magnitude here, and so I have 30 here, 30 here. They will go cancel with this 10 to the negative 6. So eventually it's going to be, if I times them, it's going to be, comes out at 10 T. So I have 1000, 1000, and then I have 10 to the negative 6. So these three will be canceled out. So only 10 will be left. For the second term, this one is going to be times this one, and this is 0 times whatever is going to come out at 0. And for the third term, this is what I have here. Again, I have 20 here and 20, so 40. So, and then I have 1, so it's going to be 10 to the negative 1. And then if I simplify that, if you times this by this, what eventually we are going to get is going to be 2.5 T to negative times 5. So the 20 here, 20 here, and 10. So 5 of the 0 which goes with 5, and then we have 5 times 5 is going to be 25 times 10 to the negative 1. So it comes out at 2.5, or you can write it 25 times 10 to the negative 1. And then we have a negative sign here, and then it's going to be the other way around. Or I can write it, maybe let's write it the way it is, so it's not that confusing. So it's going to be negative 25 times 10 to the negative 1, 5 minus T. So it's going to be 0 and 1. It's going to be between 1 and 3, and it's going to be 3 and 5. And then if we want to calculate the energy, we have different equations to calculate the energy, but one of them, again, we can use the half of C V squared times T. So we have the C, we have the V, and we can just simply calculate that. So the energy in this system so to calculate the energy for the first one, so we have the half of the C, which is going to be 10 times the -6, and then the voltage, which is going to be 1000 T to the power of 2. And then for the second one, again, we have the half of 10 to the 10 to the -6, is half of C, and V is going to be times 1000 power of 2, and the same for the third one, -6, and then this equation here, 500 times 5 minus T to the power of 2 again, and this one is going to be between 0 and 1. This one is going to be between 1 and 3. And this one, I write it here, it's going to be between 3 and 5 seconds. So basically these are the three that we have. So we have the voltage here that this is what we known, and then we have the power. So we calculate the power on top of that, and then we calculate. So here, the voltage is what we know. Then we calculate the current from there, and then we calculate the power and energy from there. I'm gonna try to show how these are gonna look like on the plot. So if you have the V, try to draw it here. It's going to be the V, and then we are going to have the so it's going to be V, I, P, and U. So P, and then it's going to be the energy. So for the first one, if I draw the voltage, and let me say it's 135, so I think it's going to be 1, 1, 2, 3, 4, 5. And then we have 1, 2, 3, 4, and 5 here. And just say 1, 2, 3, 4, and 5. And then 1, 2, 3, 4, and 5 here. So for the voltage, what we have here is that it's going to 1000 T. So for when the T is 0, it's going to be 1000. So it's go up to 1000. Then it's going to stay between 1 and 3 as 1000. And then it goes back to 0. So if you put the 3 here, so 5 minus 3 is going to be 2. 2 times 500 is going to be 1000. And if you put 5 here, it's a 5 minus 5. It's going to be 0. So it's going 0. So it's going from here it goes back to 0. In this case, so this one is going to be 1000 volt here, and then it's going to be 1, 3, going to be 5, 1, 2, 3, 4, and 5 seconds. So the voltage is going to change like that if this is going to be the T for all of them. And then if I go ahead and plot the current, for example, here you can see the current that we have. So if I go and plot the so we have 1, 2, 3, 4, and so it's 10 to the negative 2, basically, and so it's going to be like that, and then it drops down to 0. Then it's going to be 0 between 1 and 3. And then it becomes negative. So yes, it goes down, goes back here between 3 and 5, and then goes back up. For this case, gonna look like this. So this is going to be the eye, how the eye is going to look like. And then the next one, if I bring it a little bit lower. So the next one is going to draw the P value. And the P values is 10T, so it's going something like that. And then it becomes 0. So it suddenly drops, becomes 0. And then if you draw this equation, you will get something like this. And this one is going to be a little bit higher. So let me correct that. This probably goes up to here. Goes like that. It drops. And then for the this one, if we draw that one, the energy equation, it's going to look like that. Look like something that it's increase up to this point. So it's increase like that. Then between 1 and 3 is going to stay constant. And then here it's going to be decreasing back towards 0. Now, well, you can put the values here, but more than the values of how the values of this plot, I want you to pay attention to form of the plot. So in this part, when we have the voltage increasing in the system, as you can see, so we have the current because we have the change in this voltage, as this equation shows here. Because there's a change in the voltage, there is a current in the system. So there's a current, and because there's a current, the capacitor is actually being charged. So it's going to be, I would say, the electrical charge is going to be built up on the capacitor. So you see, particular here, the energy inside the capacitor increase. So as long as the voltage is changing, the capacitor is charging and charging and charging. As soon as the voltage becomes constant, then because of this equation, as soon as the voltage becomes constant, if for example you have the battery and it gives you the constant voltage, as soon as the voltage becomes constant, the current drop to zero. Basically, the capacitor doesn't let any current pass through it anymore. As soon as the voltage becomes constant, it doesn't let any current goes through. And then because the current not go through, the energy stay constant. Whatever energy build up to that point is gonna store that energy and keep the energy there. And it's gonna be the same as soon as you see the voltage start to drop and goes back. So the current in the capacitor is gonna be negative. In other words, the capacitor starts to contribute or start to fight the change in the system. So it start to release or gives back the energy to prevent the drop of the voltage. And eventually it gives all its energy back until it becomes zero. There's no energy left into that. So you can see all the energy goes away. So in other words, when the voltage is changing and increasing, it builds up the energy. When the voltage is constant, it just store whatever energy it has and keep it the way it is. And as soon as the voltage changing and dropping, it starts to release its energy to fight back the voltage drop, and eventually it releases all of its energy back to the circuit. Okay, now I'm going to talk about what's happening if we put some capacitors in series or parallel respect to each other. Remember, we had the resistance, and we said what's happening if you put a couple of resistors in series, or what's going to happen in a couple of resistance in parallel. The equation that we have for the capacitors is like the opposite of what we had for the I would say for the resistance. So if you have a couple of capacitors, it's going to be in parallel. So I would say this. So if I have, let's put it in series first. So if I couple of capacitors going to be in series like this. So it's going to be C1, it's going to be C2, it's going to be C3. I can replace them with the single capacitor and call it the equivalent capacitor. And then that is equivalent capacitor is opposite of the way we write it for the resistance. So in resistance, when they were in series, we add them. When in parallel, we just do that equation. Now it's here's one doing what. So it's going to be 1 over C1 plus 1 over C2 plus 1 over C3. And the same if we have the capacitors are going to be in parallel, like that. That's going to C1, C2, and C3. So if we have something like that, again, I can go ahead and replace that with a single capacitor like this. I call it again the CEQ. And this time, as I said, we are doing the opposite way of we are doing it with the resistance. We just, if it's going to be C1, it's going to be C2, and it's going to be C3. So we just add C1 plus C2 plus C3. So we just, if they are in parallel, we just add them together. So this is how we deal with the if we have the capacitor in parallel or resistant. The other things is going to be similar to what we have before. For example, the current, if you have the current goes here is I, so we are going to have the I1 here, we have the I2 goes here, and then we have the I3 goes here, similar to what we have before. If the same here for the in the series, if there is I, because they are in series, if there is I, the I is going to be the same in all of them. The same again if for the voltage, if the voltage and these two end is going to be V, is going to be V in first one is going to be V, in the second one is going to be the V in the third one. So the voltage is going to stay, assume it's going to be V here, it's going to be V here as well, it's going to be V here as well, it's going to be V here as well. So they have the same voltage. But when they are in the series, we know that in the series the current is going to be constant. So if I have, let me draw that here. So if I know that it's going to be I going through here, so it's going to be the same I here, so the same I here, same I here. So whatever going through is the same, but the voltage then is not going to be the same. So it's going to, here I have the V1 as its voltage, the second one is the V2, and the third one has the V3. So each of them has its own voltage, but the current is going to be the same. So it's going to be V1. So the other is the same as what we had before. I'll use another color here, so I'm not going to get confused with. Yeah. So separate them with this. So this is how we have it. Except for these two equations, the other facts that we had is the same as we had before. But here for the I and V, but the equation is kind of the opposite of what we had before. So let's look at an example to see how it works. Assume we have a circuit like that. So have the 6 microfarad here. Then it goes, and then it goes here, and then we have 4 microfarad here. And then we have 12 microfarad here. And then we have 24 microfarad. And so I assume we have a circuit like that. So for example, it's connected between these 2 points, and then want to find the equivalent of that. So if you look at this circuit, we know that at the very beginning, these 2 are, as we said, in series. So I can go ahead and say, if it's, for example, it's A, and it's going to be B. So I can go ahead and say, okay, I first replace these 2. So I'm going to have the 6 here, then I have the 4 here, and then I have these 2 in series. So I'm going to put the very first one here, and they are in, I replace these two with the one here, and I would say that, for example, here, the C for this one is going to be 1 over 1 over 12 plus 1 over 1 over 24. So this one is equivalent of this and this. And if I do that, it's going to come out as 8 microfarad. Now that I have it like that, I can go ahead and say, okay, now these two are in series. So I can go ahead and say, I would go ahead and replace these two with the single one. So it's going to be, again, I have this 6 here. And then I have these one that replace these two. So this one is going to be replace these two. So then I'll go ahead and again the equivalent one is going to be here because they are parallel. So it's going to be just add them together. So it's going to 4. This one is 4, and this one is 8. Just add them together, and it comes out at 12 microfarad. And then again we have these two is going to be in series, so I can go ahead and say I would replace these two with a single one. Like that. So again, these two are in series, so it's going to be the C is going to be 1 over, so it's a 6, so it's going to be 1 over 6 plus this one is 12, so it's going to be 1 over 12 and becomes 4 microfarad. So we can reduce this original one into this single capacitor. It's very the same, except for the formula. The procedure we take is very the same as we have for the resistance, so it's not that much different.